Hi guys, welcome to God Academy. In this lesson, I'll be taking you through the second example of type 1 mathematical induction problem. In our previous lesson, I introduced you to mathematical induction and we solved our first simple example. In this example, it's a little bit complicated. Stay glued to your seat and watch the video to the end. Please subscribe if this is the first time you have been on this channel. Prove that the statement 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared is always equal to n multiplying n plus 1 multiplying 2n plus 1 all over 6. How do we prove that this statement is true for all positive integers? That is the question of mathematical induction. Quickly, the first step, base step. In the base step, we prove for the basic. So here you say that let our statement be equal to p of n. Okay, let p of n be equal to the statement. Okay, so 1 squared plus 2 squared plus 3 squared plus n squared should be equal to n multiplying n plus 1 2n plus 1 all over 6. Okay, so for our base case, we say that proving for n is equal to 1. Okay, so when n equals 1, we are looking at the first term of this series. So if you sum the first term of this series, then we put 1 wherever we see n on the right side, it should be equal to confirm our base case. On the right side, you write your left hand side. So on our left hand side, we simply have LHS, and that is equal to 1 because 1 squared, because the first term 1 squared is simply equal to 1. Okay, on our right hand side, what do we have? We have this, wherever you see n, you put 1. Okay, 1 1 plus 1 2 multiplying 1 plus 1 everything over 6. This gives me 1 multiplying 2, this gives me 3 multiplying 3 all over 6, which is also equal to what? 1, because this will give 6. Therefore, the left hand side is 1, the right hand side is also 1. So our base case is true. So we write therefore base case is true. That's all. The next step is our induction hypothesis. So number 2, induction hypothesis. So with the induction hypothesis, you write that assuming the statement, or you can say the statement p of n is equal to, the statement p of n is true for n equals k. Okay, so the statement p of n is true for n is equal to k. Therefore, my statement p of k, because now we are saying that it's true for n equals k, becomes 1 squared plus 2 squared plus 3 squared plus 3 dots plus k squared. Okay, is equal to k multiplying k plus 1 multiplying 2k plus 1 everything over 6. At this step, it's just an assumption, so we assume that this whole statement is true. Number 3 is what we have, the inductive step. Inductive step is the actual induction. Okay, so proving for n is equal to k plus 1. As we did in our previous lesson, you were right. So now you have p of k plus 1. Then we are going to have 1 squared plus 2 squared plus 3 squared plus. Now we are looking for the next term after k. Okay, so this k squared here remains. We are looking for the next term. You realize that in the first substitution, here was n squared. It was a placeholder for any number of terms. And we claim that at n equals k is true. So replace it with k. Now, at n equals k plus 1 is not a new term, but it's a term after k. It's k plus 1, right? So meaning we're going to have our k still remaining, then plus another expression k plus 1 all squared. Should be equal to, now on our right hand side, wherever we see k, we have to put k plus 1. So you have k plus 1 outside for this k, right? That's what I have here. Then I also have into brackets k plus 1 plus 1. That is for this bracket. That's for this bracket, okay? Then I'll have close bracket multiplying 2 times k plus 1, okay? So my 2 k plus 1 everything over 6. The goal from this level is for you to prove that your left hand side is equal to your right hand side, as simple as that. But before then, you realize that from here to here is the same thing as we have from here to here. And since our assumption is true, we simply carry what I have here to this end, okay? So I simply have k multiplying k plus 1 multiplying 2k plus 1 all over 6. I'm substituting what I have here to here because it's the same. This expression plus what I have here, k plus 1 all squared, should be equal to k plus 1 outside. This become k plus what 2. This become 2k. Now you get 2 plus 1, right? Plus 3 all over 6. As simple as that. We go ahead to simplify. And at this point, what do? You simply cross multiply. Simple algebraic expression. So I have k multiplying k plus 1 multiplying 2k plus 1 close brackets plus 6 times multiplying k plus 1 all squared all over 6 is equal to k plus 1 k plus 2 2k plus 3 all over 6. So what do I do here? I'll expand this and I'll have my k squared plus k multiplying. So here we can also do something simple here, but let's expand everything. So k squared plus k, 2k plus 1, right? Plus this becomes, let's expand this, 6 open brackets, k squared plus 2k plus 1, right? Everything over 6. Then because of that, let me expand this side to this side, this multiplying this, I'll have k squared plus k times this 2k, plus 1 times k, that is k, then plus 1 times 2, plus 2. All this multiplying 2k plus 3, all this over 6. So I move forward to simplify. I'll have this here. Now, this and this gives me 2k cubed, right? Plus 2k squared plus, then the 1 comes, k squared plus k, right? Plus here gives me 6k squared plus 12k plus 6, right? All over 6 should be equal to my right hand side. Now this also multiply this. I have 2k cubed times this. I have plus 4k squared. I have times this plus 2k squared. I have 2k plus 4k. So plus 4k times 2. Then I have plus 3 here, okay? The plus 3 is also going to add 3 times the first one, 3k squared, right? Then I have 3 times 2 plus 6k plus 3 times this k, 3k, then plus 6, right? All this over 6. Now let me simplify so well here. So at this level, I'm adding. I have only k cube is 2k cube, so 2k cube. Then the only k squared is what? 2k squared plus this or 3k squared, right? 3k squared. And I also have another 6k squared here. So that gives me what? How many k squared? That should be 9k squared. So plus 9k squared. Then what else? K. I'm left with this k. I'm left with this k. That gives me 13k plus 13k. Then I have my plus 6 here. All this over 6, right? Should be equal to here to the same. I have 2k cubed. I have 4k squared plus 2k squared, 6k squared plus 39k squared. Then plus my k. I have 4k plus 6k. I have 13k. Then finally plus 6 all over 6. Finally, we are done. So we say that our P of what? K plus 1 is true. Therefore, the conclusion is that our statement P of n from the problem is true for all positive integers n. Thank you for being with me in this video. Don't forget to like, subscribe, and share. See you in the next lesson.